For our second problem, which is actually a lot simpler than the first one, we have this system where a mass is supported by two cords attached to walls or supports. The first cord is inclined at an angle to the upper wall, while the second one is perfectly horizontal. We'll call the tension in the first string T1 and the tension in the second string T2. So our first step is to draw the free body diagram. And we're going to draw the free body diagram of the point where the strings meet or where they are joined. So doing that, we have our T1, we have our T2, and we have the weight of the attached mass. The weight of the block is equal to 190, which is its mass, multiplied by the acceleration due to gravity, which is equal to 9.8 meters per second square. And this is equal to 1862 Newton. Since this point is stationary, it's in equilibrium, and we can say that the sum of the horizontal and vertical forces acting on it is equal to 0. So starting with our horizontal forces, taking the right direction as positive, we can say that the sum of horizontal forces is equal to T2 minus T1 cos 33, which is the horizontal component of the tension T1. And this sum is equal to 0. So we can write T2 equals T1 cos 33. Now we can write this as our equation 1. So the sum of vertical forces now, taking the upwards direction as positive, is equal to T1 sin 33, which is the vertical component of the tension T1, minus 1862, which is the weight of the mass, equals 0. So T1 sin 33 equals 1862, and T1 equals 3419 Newton approximately. Substituting this value we've obtained for T1 into the first equation we got, we can find our T2. For our final problem, we have a uniform rod of length 5 meters and mass 3.8 kg, hinged to the wall at point A and held in equilibrium by a cord as shown. A load of 22 Newton hangs from the rod at a distance d, so that the tension in the cord is 85 Newton. Our aim is to find the reaction forces at the hinge and the distance d. Our first step here is to draw the free body diagram of the rod and indicate all the forces acting on it. We'll start with the weight of the rod. The mass of the rod is 3.8 kilograms, so its weight will be its mass times the acceleration due to gravity. And this weight acts on the rod at its center of gravity, which is located at the midpoint. Next up is the 22 Newton weight, which acts at a distance d from the hinge A. Next, we have the tension from the cord acting at the other end, inclined at an angle of 37 degrees from the vertical. We know that when the 22 Newton force acts at a distance d, the tension is equal to 85 Newton. Lastly, we have the reaction force at the hinge. Again, I'll represent it as its horizontal and vertical components, RAX and RAY. Now that we've represented all the forces on our beam, we can use our equilibrium equations to determine the unknown. The sum of our horizontal forces, taking the right as the positive direction, is RAX, which is the horizontal reaction force, plus T sin 37, which is the horizontal component of the tension. Our horizontal component of tension here is T sin 37 and not cos 37, because in this case, 37 degrees is the angle of inclination of the tension to the vertical, as opposed to the horizontal, which we're used to. The tension is equal to 85 Newton, so we can write that RAX plus 85 sin 37 equals 0. And we obtain RAX to be minus 51.15 Newton. We've obtained our horizontal reaction force as a negative value, but what does this mean? Well, in our free body diagram, we didn't know the direction of the force since it was an unknown, so we just assumed that it points to the right. But the negative sign from our answer indicates that the force actually points to the opposite direction, which is the left. Now we move on to the sum of our vertical forces, taking the upward direction as positive. And the sum of our vertical forces is equal to RAY, which is the vertical reaction force, minus 22, which is the applied load, minus 37.24, which is the weight of the rod, plus T cos 37, which is the vertical component of the tension. And this sum equals 0 to satisfy the equilibrium condition. So we can write that RAY equals 22 plus 37.24 minus 85 cos 37. And we obtain RAY to be minus 8.64 Newton. Again, we have a negative value, which means RAY actually acts downwards instead of upwards, which we assumed initially. To find the distance D, we can calculate the total torque about the hinge A. The first torque we have is due to the 22 Newton force, and its perpendicular distance from hinge A is equal to d sine 53. We take its torque as negative because it tends to turn the rod in a clockwise direction. Next is the weight of the rod, which acts at its midpoint. Its perpendicular distance from hinge A equals 2.5 sine 53 meters. Again, we'll take this as a negative torque since it's a clockwise torque. The next torque is due to the vertical component of the tension, which is equal to 85 cos 37 degrees, and its perpendicular distance from hinge A is equal to 5 sine 53 degrees. It's a positive torque since it turns the rod in an anti-clockwise direction. The last torque we're going to consider is due to the horizontal component of the tension, which is equal to 85 sine 37 degrees. Its perpendicular distance from hinge A is equal to 5 cos 53 degrees. And this torque is clockwise, so we take it as negative. And so the sum of our torque, taking anti-clockwise torque as positive, is equal to minus 22 times d sine 53, minus 37.24 times 2.5 sine 53, plus 85 cos 37 times 5 sine 53, minus 85 sine 37 times 5 cos 53. Solving this further, we can write minus 17.57d minus 74.35 plus 271.07 minus 153.92 equals 0.